Okay, so you can hear me? Okay, so hello everybody. My name is Marwa Tarchouli. I am a research engineer at ATEME. Today I will be presenting a chain nerve as a neural video codec. So first I will start with the introduction and some context to neural video compression. Then I will present a chain nerve as a neural video codec. So I will present its architecture and explain how it works. Then I will show an objective and visual comparison against HEVC. And finally, I will wrap up with the conclusion. So, video compression has been steadily advancing since the 80s, releasing several video coding standards through the years. The latest codec is VVC. It's issued in 2020, and the work on the next generation of codecs, ECM, are currently ongoing. So all these codecs are based on the same structure, that is this one, that is improved and pushed further with each new generation. So there are several ways to include deep learning or AI into a codec. It can be as a pre or post processing tool of an existing codec, or as a neural tool inside a traditional codec, or as the foundation of the entire codec. And in this case, we call them end-to-end neural codecs, and they are the main focus in this presentation. So end-to-end neural video compression has started in 2090s with the first model called DVC, followed by several advancements that steadily improved coding efficiency. So in just 5 years, neural codecs went from performing below AVC to outperforming VVC in some configuration. In the literature, we distinguish two categories of neural codecs. The first, called the hybrid video codec, they regroup codecs that aligns with traditional schemes, so including motion estimation, motion compensation, and residual coding, except each step is achieved by neural networks, and more specifically, variational autoencoders. So these codecs are large models. They are trained on large data sets, and even though they manage to have a coding efficiency that outperforms VVC, as I showed earlier, their complexity is very high, and they are demanding computationally, which make their deployment in real applications very difficult. So as an alternative, we have the second category called implicit neural codecs. The core concept behind it is to use a light decoding model that will be overfitted individually to each input sequence. So the encoding in this case consists of training the model. The resulting weights are transmitted into a bit stream, and the decoding process involves retrieving those weights and applying them. So this technology prioritizes low complexity on the decoder side at the cost of longer encoding times. So in this talk, we will be focusing on implicit neural codecs, and more specifically on NERV models. So NERV is an implicit model proposed in 2021. The architecture is shown here. So basically, the network takes as an input the temporal index of the frame and generate the corresponding frame. First, there is a positional encoding step that transforms the temporal index into a higher dimensional vector, which will be encoded by MLP layers. And then we have decoder blocks here called NERV blocks that generate the corresponding frame. They are based on convolutional layers, one convolutional layer, one upscale layer, and one activation layer. So this model was a baseline for multiple other models such as eNERV and HANERV. So as you have assumed, we will be more talking about HANERV as it shows one of the best performance in the state of the art. So here we have ATEME. Globally, its architecture resemble nerve. However, it has a patchwise approach, meaning that as an input, it doesn't take only the temporal index, but also the patch coordinates. Also, positional encoding is replaced by a feature grid that is learnable during training. And then we have decoder blocks that also have a convolutional and upscale layers, but it is based on complex layer, which is more sophisticated and show better performance than classic convolutional layers. So here we show the several steps of ATEME. The training process has three phases. The first one is classic training. So we apply a forward pass. When we apply the model, we compute our loss, which in this case is a combination between the L1 loss and the MSIM. And then gradients are computed, and backward pass is achieved. After that, we apply pruning, which consists of eliminating redundant and less important weights. It managed to reduce the size of the model, and this is practical because we transmit the model, so we want it to be we want it to be the size. We want it to be the size as smaller as possible. And finally, we have quantization-aware training, in which we train the model to be more robust against quantization. So how we do that? In the forward pass, we apply a fake quantization, and on the backward pass, we compute gradients and update the weights using the unquantized values. So after the training is done, and in this case training is the encoding, the resulting weights will be transmitted, and in here we apply uniform quantization and entropy encoding to have compressed weights. But since we used in the training quantization-aware training, when we apply quantization afterward, we don't have the performance is not altered. And finally, the decoding process includes entropy decoding and the model inference. So here I show some objective results of ATEME, starting by rate distortion comparison between ATEME and the HEVC. So HEVC is the green curve, and the ATEME is the blue one. So in some sequences, such as this one, the first one, both models have approximately the same performance. On others, HEVC is better. In this one, it is the worst case scenario. There is a great gap between HEVC and ATEME, but globally, HEVC is still better. But ATEME is closer compared to other implicit codecs. I also show some complexity results. It's more to give an order of magnitude. Here we compare it to HEVC, but it's not very comparable since it's run on CPU and the others are run on GPU. But what we can say is that ATEME is less complex than a hybrid codec. The number of multiplication is much reduced. The decoding time as well, but it's still to be optimized to match HEVC. So overall, ATEME provides a big advance compared to other implicit codecs, but it's still not mature enough to compare with HEVC. Nevertheless, visual results show some interesting behavior and artifacts, so we're going to present that. So if we take this sequence as an example, it has high-frequency features on the boats. The water part is also tricky, and we're going to compare ATEME against HEVC on 2 megabits per second. So if we zoom in, we have this part. So on the water parts, HEVC have some blocking artifacts that spoils the video visually. while ATEME provide a much smoother reconstruction. On the both part, HVC preserved more details, but ATEME it has less details. It lacks fidelity, but it doesn't spoil the video. It's still smoother to watch overall. So the overall rendering is much smoother with ATEME than HVC. And here I will try to just launch the video. I'll let you see. Okay, so now I will go to the second sequence. So it's a rugby game, which means there's a lot of movement in it. And we're going to do the same comparison on 2 megabits per second. So if we zoom in, here HEVC have some ringing artifacts, which is somewhat not surprising. But ATEME have the same smoothing effect, except it's not positive in this way. Sometimes we barely distinguish the player's head, and so it's too smooth. And also there is another limitation, which is temporal instability. It is we can see some flashing artifacts, which means that the model has trouble with temporal correlation between the frames. So here also I will let the video play. I hope you can see what I'm talking about. Okay, sorry. So if I summarize this visual comparison, we can see that ATEME show different artifacts than the usual traditional ones, such as blocking and ringing. In fact, ATEME prioritized smooth rendering over fidelity. And in the first sequence, it worked well, meaning that the overall rendering was better than HEVC. But even despite the lack of fidelity. However, for the second sequence, the smoothing effects spoiled the video, and it also has another limitation, which is related to temporal instability. So to wrap up, in this talk, I presented ATEME as a neural video codec. I showed its architecture and explained how it works globally. I also provide some objective and visual comparison against HEVC. So in terms of coding efficiency, ATEME is still not mature enough to compare with HEVC. However, it does show some great potential for neural codecs. And on the other hand, visual comparison shows some interesting behavior. In fact, ATEME prioritize smooth rendering over fidelity, which sometimes can be better than blocking and bringing artifacts. But it does have other limitations, notably temporal instability and difficulty with the fast motions. And that would be all. Thank you. If you have any questions,
she cannot hear us. Thank you, Marwa. Do you have any questions?
Thank you for the presentation. Have you done any tests with generative AI content versus natural content? Because all the examples you were giving us were about natural content. Is there any benefit for Gen AI content?
Can you repeat the question? I can't really hear.
The question was, did you test it on Gen AI content, see if it worked better than versus real content?
Not really, because we at ATEME were more interested in natural content. What we did is some other test on UVG dataset, which is still natural content. what I observe personally, it's sometimes the reconstructed video of a chain nerve. It has some similar features of a GNI content, but it's more personal opinion than a conclusion.
Thank you.
A lot of the metrics we're using to compare codec performance are based on the same reference model of the last 20 years. With those new types of codecs, do we need some new metrics as well, like a new version of VMAF, like a new version of PSNR, which takes those new reference models into account?
Did you hear it, Marwa?
I think so. So here we use two metrics, PSNR and MCSIM. So we didn't use other perceptual metrics such as VMAF or other neural metrics, but it is on our list in the future works. I think it would be interesting to show some other metrics and also to train the model to optimize those metrics.
No other questions? Oh, yes.
So I assume that this codec is more of a delivery or final output codec. Is this something, given like the super long runtime we had with H.265 HEVC from, as your presentation said, 2013, just now we're getting, or over the last few years, we've really started to get devices capturing in H.265. I guess first, could this ever be used as a capture codec as well? And then is it going to be primarily software or hardware? Like will chip makers have to implement some kind of hardware encode decode engine on chip to use this in potentially real time?
So correct me if I didn't hear correctly, but if this work is still in research, so we don't have quite an idea where we going to put it on hardware or software. I'm going to go with software because that's what we do at ATEME. But we're still not. We don't have some real application results, meaning if its complexity is doable on a phone, on a server, on other things. So we mainly focus on the coding efficiency at this stage, since it's still not mature enough to think about other aspects, I think.
Thank you very much. Thank you, Marwa.
Thank you.
Robin?
Nos vies.
Hi everyone. So tonight I'm presenting our startup with BJ over there. We spent the last year building a tool that we slowly evolved toward a full agentic video editing flow. It's called Tellers.AI, and so like comes from the obvious statement that like video is everywhere online. It's the main content, and everyone, all businesses need to create video. Yet video editing and video creation is still very slow, heavy, and expensive for most people that are not experts. So our vision is to really create this assistant that can help you create videos, or at least first draft, or derush your videos or your footage. And the way we describe it now, since a few weeks, is the cursor for video editing. So how many of you know Cursor? Yeah, so basically it's the AI assistant that we have like in a code editor, and that can just code alongside what you're doing. And being a startup and being short on time all the time, we use it a lot, and we really started to like it a lot, and we realized that it was obvious that video editors needed a similar tool, which is similar in many ways. Editing and coding is very similar in many ways, but you still have all the video infrastructure that you need to plug in and some added complexity. So what I want to propose today is that we rebuild Tellers together from the start, so you can follow a bit our journey. So it's a game. We will unlock each level for each slide. So let's start with creating a video player. So very easy, no problem with that so far. Now, if we start with like a very basic editing task, let's say we need to like search for videos. So what we could do is just add a video library or maybe stock footage with labeled data, with description or keywords or date ranges, and we can do simple art filter search on it. Still easy. So now you have stock footage in your application, you can select your video, but still very limited. And the search is not that good actually, because if you're like a normal human being, when you search for something, you want to describe it. And just having like knowing all the keywords or all the label in your database is very tough. So obviously we need something more to be able to describe what we are looking for in natural language. So I'm sure many of you already know what are embeddings. You all seem like very good AI experts. But here's a quick reminder. So embedding is just like a geometric representation of data. So it can be a video, it can be a part of text, it can be any data, really. And then the task of the AI is to create a space or like a function that will transform your data into like a data point in a high-dimensional geometric space, and make sure that all elements that are semantically related are close to each other, and the ones that are very different are far from each other. This allows us to so it's the most obvious case is for like same modality, so text to text when you search. But since a few years, you can also do it across modalities, so like searching like with a text query that you embed with the AI, and then it will be matched in the space with embeddings of videos, for instance. And then all we need to do is do like a comparison. So you optimize it in databases now, but the rough idea is that you compare your embedding with all the other in the database. So like you have your query, someone holding a pizza in the street, you embed it, and then you will compare it to all the embeddings of the videos, and the closest one will be the one that matches the most your query. So we can, happy to dive into the details later, but still very simple. But what's nice, and many people miss with embeddings, like just using it for search, and it's very accessible, it's like a commodity now, you have tons of open source projects and models, is that you can really play with it. And this is like it's a 10-year-old like example of having a king vector minus a man and plus a woman, and then you get a queen. This is like the base example, but you can really play with your embeddings and create like a batch of embeddings, average them together. So if you have like 10 different queries and you want to like average them together, you will find something that's like the video most related to the average of everything that you were searching. Or you can embed the full context of your project and like a local query, and then you will get the most relevant video. So yeah, quick insight. If you add dimensions, you get more space, like the volume is increasing non-linearly, and like my intuition is that the more dimension that you add, the more ways of being or making stuff dissimilar you create. So it's yeah, we can talk about that after. Yeah, quick pointers if you want to look at more embeddings after the conference. But yes, now we unlocked search with AI, and so now you can search anything by describing it in natural language. So we are still far away from a full video editing platform. And now also, yeah, you want to be able to upload your own videos because you don't need labels anymore. You can just let the user upload these videos, and then the AI will automatically create the embeddings and let the user search through them, even without any label. But yeah, now let's actually try to edit something together. So our first use case, it was actually for journalists. We are turning articles into videos, but this is the most basic one I can present. So let's say you have a podcast and you want to turn it into a video. So you have like a very simple way to do it. You just cut the audio, you define the chunks, and we can do very clever stuff with that, but let's just say you find some way to chunk your audio. You will just transcribe it, get the text, and then just search for like a related video. And then you will have a matching timeline that matches the audio that is being spoken. Still very simple, but it unlocks many other use cases. And if you are smart with your embeddings and the way you handle context, it's still very powerful. But that's still very fixed. So you give it like an audio, but you don't have control. You can't tell it what you want, what is your style. So now we need to use LLMs. So I'm sure you're familiar with LLMs, so like ChatGPT and AI alike. And want to be able to give a query like make me a viral video. So at least so it can try to do it. And then the AI will basically describe scenes with audio that you can either match in the database or generate with AI and the search query. And then you can create like a video that has more control. So you can say, okay, I want only videos of nature at the beginning and stuff, and then you mix your queries and you let the LLM or your regular ChatGPT create the overall structure of the video. Okay, now the fun part and very related to video tech, and we are kind of noobs in video tech from when we started the project, so we learned a lot and we hit a lot of walls. So when we want to start letting the user edit the videos, well, it's nice, now we have a timeline, but it broke our video player. So like it's like a sub-story, so like the rabbit hole of our video player. We spent much more time than we wished on the video player. We re-implemented one. So this is our base, like trivial integration of video. So we have our files that are stored, and then the backend is rendering the videos together. So you take like all your playlists, you put it together, and you send it to the front end. You play it in a regular player. It's like straightforward, but not very flexible. So then, when we want to like send the chunks to the front end, so that the user can edit them without having like tons of rendering in the backend, you can pre-chunk it. But then you need like you start needing to have like a custom export pipeline, which will not always match perfectly with the preview. And you still have the stitching to do in the front end, which we used to do in FFmpeg wasm. Which was nice, but still needing back and forth with the backend whenever we wanted to change the length of the videos. So after we used video chunks and range requests, so we didn't like we downloaded less videos at least from the backend before normalizing and cutting the videos. Then we moved to we removed the server processing and only sent chunks to be processed by the front end, and always fetching with like range request on our storage. But we still had the custom export pipeline. And then that's when we decided to really go all in and re-implement our custom player with our custom caching and frame handling and decoding, which let us actually read the timelines in real time without any lag between the videos. And actually it also solved the export problem, and now we can guarantee that whatever you see in preview is exactly the same as what is going to be exported. Which also unlocks use cases when we will start adding motion design later on. But that's another story. So this is a quick, maybe I'll show it later. Quick demo of our custom player. We can like play and do picture-in-picture real time with many different footage from different storages. And that fixed the export and the video player. And now we go into the core of what we are doing, so the agent. So for those who use Cursor, it's what you have on the right side of your code editor all the time, or very similar to ChatGPT. And it's very trendy topic. Everyone is talking about agentic workflows, which makes sense because it's very powerful. But we needed to rethink our tech. And so, yeah, okay, so what is an AI agent basically? It's ChatGPT or a large language model. You give it tools. So for instance, in our case, you will give it tool to edit the timeline or search for footage. And then you just basically put it in a loop and the agent will tell you, okay, I'm done. And then you cut the loop. So for an overview of what we integrated as tools in our timeline, which is like a whole new field of engineering and expertise to define the proper tools for your help. It's basically finding the most elegant abstraction and make the tools as simple as possible and remove as much complexity from the LLM reasoning so that it can focus on the style and the overall creation of the video. And so the tools that we integrated is the search in stock footage that we created together earlier. Then the search in the user video, we can match the dialogue with real clips. So if you have like thousands of hours of video and dialogues or podcast, then we can automatically find when someone said a specific thing and add it in the timeline if it was in the script. We can insert clips in timeline, do editing, so the agent has all access to the editing timeline. So if you want to shorten all your clips by 1 second, or if you want to tell the agent to spend 30 minutes finding the best match with the text and try different stuff and rewatch the video, well, you can. And we also have tools to align the cuts with the music that can be used by the agent. And now, the unforeseen part, we really started this project to create videos from real footage because it was the start of AI and it was not so good and very expensive, very slow. And so our core focus has always been in creating video edits, and we have developed custom models for that and for context search and for cutting and detecting the good rhythm. But this new agent allowed us, once we have this player that allows us to preview and export with nice consistency, do that in a web platform very easily, then it opened the door to like integrate all the different AI models that are open source or private inside the agent. And now when a user wants to edit a video from his footage, he can just drag and drop the folder in the chat and say, okay, edit a timeline from this folder. Or it can ask to tell a story from just AI-generated videos, generate the music, create different projects. So all in the same chat, you can just ask it to create 10 different projects in 10 different languages. So it's like really something that you should see as like a background task for now, because all video processes generation are very slow. So it's not as fast as what you do with Cursor, but it's still very powerful. And quick tips on what we call context engineering now, because prompt engineering is not fancy enough anymore. So are you all aware what system prompt is? No? Kind of? Okay, so the system prompt, when you design an agent or an assistant, it's like a part of the prompt, so basically a message that you send to ChatGPT, that will have a lot more priority when the agent, when the AI will follow the instruction, compared to a message sent by the user. So that's a very nice innovation. That's like maybe 6 months or a year old. That allows you to differentiate between like the messages from the user and what you want to instruct the model to do. So for instance, you could tell it, okay, never create a script with bad content or weird content, and then if the user asks for it, you can always jailbreak it, but normally it will follow the system prompt more than the user request. The latest models, especially GPT-5, it really unlocked this use case because it can really do long processes. So it's very good at calling tools when you have a big list of tools and complex tools. And especially it can run for a long time. So it can spend 30, 40 minutes just calling tools and doing its work without losing too much of awareness or stop making sense. But the rising issue is that you can add more instruction and it will follow them very strictly. But the most little contradiction that you will add in your prompt, it will like break everything. So if you have a tool that is defined and that says that a parameter is optional because you defined it with like a your Python framework and you forgot that it was optional, and in the prompt you say you always have to make it, always have to put it in the tool call, then it might create very weird behavior in the agent. Delegate, so it's still code and still overall logic, so anything that you can do in code will be first faster, cheaper, and it will remove a lot of complexity from the agent so that it can focus on the most important task that cannot be done with code. Okay, sorry. And voila. So we have our full cursor for video editing. So I think it's very straightforward, but you have a lot of rabbit hole behind it. And I would be happy to answer any question. And I have like some demo videos, and we can also try a live demo. I don't know if we have time, but yeah, you can ask your questions. Thank you.
Questions?
Thank you for the presentation. It was very interesting and precise. Which model did you find was the most adapted to your use case, to the video use case? Was it GPT, like everybody? Or?
For the LLM?
Yes.
Yeah, GPT-5. It was really a game changer. So like it was funny because I fell in love with GPT-5 because it solved a ton of issues that we were trying to like contourner, to go around a lot of issues with other LLMs. And when GPT-5 was released, it unlocked everything. So it made like the pipeline much simpler, and like it's improved a lot of our performances. Actually, just before we released it, because we released it officially last week. So it's very this new agent is very new. But expectations were so high in the general population because they were shocked by GPT-4. That's everybody, like the overall feeling of GPT-5 is that it's bad or not that much better, but in fact it's very, very good at calling tool and following instructions.
And before that, you were using what?
We tried different models over the time. The one that worked best before that, and I'm pretty sure it's like GPT-5 is an evolution from that, was a GPT-4.1 mini, 4.1 standard, sorry. Yeah.
Thank you.
Yes?
We had really good experiences with Gemini versus GPT-4. Have you seen that as well, or have you tried Gemini versus that? Curious in your experience.
So we tried Gemini before GPT 4.1, and like I made the experiments when we were like struggling to find a long-running agent that were not lazy. That was the big issue basically, because if you had like a tool that required a lot of arguments or like long responses, because like a version that we had before the agent was just outputting the full video script at once with a lot of details. It was very, very big chunks of text, and LLMs, they have like huge context windows, so theoretically they can output 120,000 tokens, but because in the training they only see examples of like very small outputs, it was very hard to like instruct them to like output a video that would last more than 30 or 40 seconds. So that was like the biggest issue before. And at that time I tried like all the LLMs out of desperation. I haven't tried the latest Gemini models. For this use case, I tried it with, like vibe checked it. Okay, nice.
Just a question, how you describe the video to the LLM? Do you send images or a description of what you get or you get through the embeddings?
That's a very good question. So it's like a two-step process, and you can actually, we are like we spent a lot of time thinking of what we could talk about, and we had like lots of models that we built. But now with the agents, it's like everything is you can see everything when you play with the application. Like the agent will show you everything that you are doing. So sorry, I missed the question.
Just what data has the LLM?
Yeah. So now you can see that it's a two-step process. So basically, it's the embedding search. It can filter on your folders, on like subfolders if you want to, like you have like, we have a drag and drop system as in Cursor. You can drop your folder and say, okay, only search in this one. And so it will do the embedding search with other filters. And then only when the agent like defines that it's important to get more better understanding, we use a VLM. So for that, we actually tried a lot of Gemini, only for the VLM. We tried 12 Labs, and also Apple just released like a new model that runs on device. It's a very small model, and it runs in real time as well. I don't know if you saw the demo. I think I have it somewhere. So you have many VLMs that will describe the video, and the nice thing is that it's prompted before, like during the execution. So if the agent knows that it needs to understand like the precise timestamps or what's happening with a specific person in the video, then the VLM will output a description that is tailored to that. So yeah.
Follow-on question. Does that VLM understand temporal or not? Like, does it look at a sequence and understand
the VLM?
Some level of causality, or is it not?
Yeah, it's very impressive. I like the first test I made with VLM when we started going agentic. Like, I was very shocked. It's incredible.
Super interesting. Thank you.
But it's like the issue, and as I said, it's video, it's super heavy, it's expensive, so we don't have subscription actually in the app. We decided to like go all in on tokens. You only buy tokens, and then you spend them when you use the application. We try to make it as cheap as possible, but it's still slow. So spending the money makes sense when it can like create a video like in 30 minutes without you looking at it, and it will spend like maybe 10 euros if you use like the biggest VO3 model. So it makes sense, but the time it takes, it's a bit annoying sometimes, especially if you want to do like back and forth. And the VLM is very slow, so like it's I think it's 4 or 5 times real time. Yeah.
Thank you.
Welcome. Do we have time for a quick video?
We have time for a quick demo. Yeah. Il est branché.
So I don't know if you like the. Oh. So this is the app. So it opens with just the agent, and then at some point when the video is when the agent will start creating the project, it will open the project. So it's made faster because it's like 1 minute per video generation. We will actually make it parallelizable, so you don't have to wait for all the individual video generation. But it's all from like a simple prompt, and I asked it to like, this is like the house of AI, and I asked it to like create a 13-second video with music. So I think you don't have the music here. And so it just like prompted the different instances of video generation, and it's also instructed to follow like camera, like same camera and same style across different shots. So you kind of solve the hard part of prompting different calls to AI, and automatically preserve coherence. And this is generated with one, so it's like an open source model, which is much cheaper. Like it's, I think, 30 or 40 times cheaper than VO3, so you can really play with it as much as you want. And we also have VO3 integrated if you want to spend big credits. And happy to do like live demo after the conference.
Thank you very much.
Thank you.
It's halftime, so pizza and beers. And demos if you want to ask Robin.
Okay, yeah, I think so. You're ready? I think so. Okay, great. So, you're starting? Yes. Okay. Yes.
So we'll restart. Just a small technical announcement. The free drinks are over. Now you'll have to pay for your drinks.
Good. Okay. Hey everyone. So I'm Tom. I'm going to give a talk on real-time video AI in the context of some stuff my company's been playing around with over the past year or so. So my background's in video. I worked at the BBC and then at Bright Cove. I'm now at Livepeer. So just to give a bit of context, because it matters later in the talk, Livepeer is a distributed compute provider where I don't know if people remember SETI at home and those kinds of projects in the early 2000s, but it's kind of like a commercial version of that where anyone with a spare GPU, maybe from a gaming rig or left over from Bitcoin mining, can bring their compute power and get paid for transcoding video. And so over the past year or so, we started looking at what if we can use those GPUs to do AI inference on top of live video. So what is real-time video AI? There are kind of two definitions floating around at the moment. One is something that can generate chunks of video faster than the duration of the chunks. So you can generate a 5-second chunk in 3 seconds. That's good for use cases where it doesn't have to be exactly real time. So for example, you have the full input ready at the start, and you could feed a text story into it, and it'll just run off and keep generating video while it reads out the story. Definition 2, which is the one we're going to be looking at, is more like true real-time, like real-time in the sense of a video call, where we're taking in some real-time input, like a live video, webcam, maybe some images, maybe some text, and then as fast as possible, we're returning video frames. So quick history of real-time video AI. It's not going to take long. It's only been around for three or so years. August 22, Stable Diffusion came out. So that's a text-to-image model. That's like, it was the first big open source one. It had that classic style of, because it was trained on a lot of computer-generated, like DeviantArt style art. It had that classic AI look, but that kind of started this big explosion of people experimenting on top of it. About a year later, Stream Diffusion came out. So that was some researchers saying, hey, like, what if we took Stable Diffusion and just generated images really, really quickly, stitched them all together, and produced a video? That actually works surprisingly well. So we'll see some examples later, but that was the first kind of real-time video experiment. Then a few months later came Stream V2V, which was building on top of Stream Diffusion, but trying to introduce some more temporal consistency. So like trying to kind of plaster over some of the problems that come with generating frames that might not look completely similar to each other, trying to make them look a little more consistent. And then this year, there's been loads of interesting stuff. Like a lot of the big players have entered. This little clip here, I think, is from one of these. So real high quality outputs, but running on $25,000 GPUs, sometimes multiple ones to produce these outputs. So that kind of puts it out of the range of like most consumers, but also like probably out of the range of anyone trying to build a profitable business on top of it. So yeah, I wasn't sure like how much people would know about this, but what are diffusion models? Basically, the way these models are trained are they have a huge library of source images. They progressively add Gaussian noise on top of it in a predictable way. And then they train the model to go back from that unrecognizable noise back to the starting image. Basically, once they do that enough times, the model starts learning about what a picture looks like. So like what edges are, what textures are, like what makes a picture. And then eventually, once it's seen enough of these, you can start asking it for arbitrary things, and it can generate stuff it hasn't seen before. But yeah, this denoising thing is the key concept here. So you can see here we've got 8 noising steps or denoising steps going backwards. Obviously, more denoising steps takes up more compute power, takes up more time, but theoretically gets you a better output at the end. Okay, so we started trying to play around with what we can do on top of this GPU network. So iteration 1 was built around this tool called Comfy UI, which is very nice. It's open source visual design tool for stable diffusion workflows. So you're basically chaining these GUI elements together to make a workflow that goes from left to right. And we'll normally start with some sort of input, like a text prompt, an image, do all the model stuff in the middle, and then spit out some sort of image at the end. It's really popular, huge library of nodes. Like anything you can do with an image, there's probably a node for it. And the cool thing is you can export these workflows as JSON. So our first idea was, what if we kind of built a hub where people could share these workflows, apply them to video, and then like try them out and play around with other people's workflows. So that's what we did first. We built this open source tool called Comfy Stream, which, similar to Stream Diffusion, is just taking a Comfy UI workflow, running it as many times as we can within as many times as we can a second, and then producing video out the other side. It can run on, in general, on consumer GPUs, so more in like the $1,000 to $2,000 range, 4090s, 5090s. Yeah, so I'll quickly show what that looks like in practice and give a little overview of like how Comfy UI works. So we've got the source image here. It looks complicated, but the main elements are source image. Down here we've got the text prompts. I can zoom in there. So we have a positive prompt, which is saying make the Hulk. We have a negative prompt that we're not using at the moment, but that could say, for example, like, I don't know, avoid cartoony style images or avoid realistic style images. It tells the model what to try and move away from. So we have the source image, the prompts, we have the model itself, and then that all feeds into this thing here, the K-sampler. This is like the core component that takes in the model, takes in the prompts or whatever else you have as a source, does the iterations, the denoising iterations we talked about, and then spits out an image at the end. The other main concept is that we have images, like we have human understandable inputs and outputs on either side. So we have an image at the end, and we have text and images on the left-hand side. Everything in the middle operates in latent space, which is kind of similar to the previous talk, like the way it described this multi-dimensional vector array. Yeah, everything in there operates on that. So we can show this. We've got Big Bug Bunny transformed into this slightly disturbing Hulk. We can come down here. We can change it to something else. Any suggestions? Spider-Man. Even better. Spider. Run it again. That's actually pretty good. And then, so this is why this Comfy UI is a really nice entry point into this stuff if you're learning it, because you can just play around, see what happens when you change things. So if we bump up the number of denoising steps, run it again, you'll see it's a little slower. We get a slightly more realistic Big Bug Bunny as Spider-Man. Yep. Okay, cool. So that's a super quick overview of Comfy UI. We can then explore that workflow as JSON. This is a little UI built around Comfy Stream. So actually, let's take the one we just made. So we export final real. Give it a nice recognizable name. And then if we go into here, load it up. This is the one, I think. Start the stream. Moment of truth. Okay, cool. So, thank you. Yeah, you can clap. So this is, obviously you're not seeing Big Bug Bunny here, right? Because what Comfy Stream is, the main thing Comfy Stream does is a thin wrapper, but it replaces the input Big Bug Bunny image with your webcam source, and then pushes the output images into a stream. So you can spin that around. But yeah, it works quite nicely. You can see. I mean, yeah, this isn't getting great FPS, but we can normally get this up to about 20 FPS remotely. Cool. So we did that. What can we build with this? Kind of anything you can do with Comfy UI, you can push into a video workflow. So the stuff we saw, like prompts to videos, you can also do style transfer where you push in an image as well, and it, like, if you push in, say, a Picasso image, you'll get like Starry Night type video outputted. You can tune it to specific styles, so you can make yourself look like an anime character. This one here was me trying out a selective blurring workflow where there's a node that estimates depth and blurs anyone, and also does facial recognition and blurs any faces in the background. And you could do like object detection as well. So a quick aside, how did we do this on remote GPUs? This gateway orchestrator worker thing is how Livepeer worked previously during video transcoding. So the gateway takes in video segments and then decides which of these remote GPUs to send them to. That's the orchestrator. The orchestrator is kind of an entity that might be multiple GPUs, and then the worker is just an actual single GPU. So previously for transcoding, we were doing this on segments. So you'd push in a 2-second segment, it'd go all the way through, get transcoded, and you'd get a 2-second segment back. So obviously that puts you like segment length behind real time. So for this AI stuff, we built out this trickle system. It's over HTTP, but it's the same kind of concept. But instead of waiting for the whole segment, as soon as we start receiving bytes, we push those bytes to the next thing in the chain, and then same on the way back. We could have done it over a long-live HTTP connection, but there are some nice mechanics like the HTTP retry stuff, and a lot of the payment stuff we do as well works better with discrete segments. So we're still segmenting on GOPs and then trickling them through. Cool. Any downsides? So yeah, you can see from this example, but it can be hard to maintain visual consistency, kind of depending on the model you come up with and depending on how you prompt it and a bunch of other things. You can end up with stuff that jumps around a lot. Because Comfy Stream's a thin wrapper on top of Comfy UI, there was no real good place for us to optimize these workflows. Each of them has to be hand optimized depending on what it's doing. And it's easy to add a new type of node in and just tank the FPS. It's slow to start because the GPU has to load the whole thing into VRAM. So if the GPU wasn't already running that workflow, you get like 30 seconds of cold start time. The fact that it's working frame to frame means you have limited scope for doing stuff like audio, anything to do with audio or anything that relies on broader context of what's happening frame to frame. And it was also just it's still hard for people to develop these things without a local GPU. So we hadn't completely removed that limitation. So iteration 2, Stream Diffusion. It was released as an open source project late 2023, kind of abandoned. I think the maintainer went to work at Google. But people were still interested in it. People actually carried on using it. It got really popular with multimedia artists because kind of like some of the limitations we saw with the original one of it being a little unpredictable and jumping around actually lend themselves really, really nicely to these public installations and things like that. It's better than Comfy Stream in some ways. It does a lot of stuff to preserve intermediate state within the workflow, especially like in the denoising, so it's more likely to generate a steady output. It's got this stochastic similarity filter on the input as well, which just means if the input's not moving, the output stops moving as well, which for a lot of things works really well. It makes it look a lot more stable. It does a bunch of other optimizations to make things faster. It does, instead of doing that denoising sequentially, I don't really understand the maths of it, but it manages to somehow do those denoising steps in parallel. And then we added a bunch of stuff on top of it as well. So we added support for new stream diffusion models, more recent ones. Control nets, which are what you are seeing here. They're kind of things that help guide the model. So they'll maybe do edge detection, or this one's doing depth mapping, but they help guide it towards a better output. We added image as prompts, frame pre and post processors. So, for example, upscaling or refining the finished product. Not safe for work filters. Like these models, some intentionally, some not intentionally, just because of what they're trained on. They really want to generate nudity. Like even if you're not trying to, they just want to. They want to put nudity in there. So we improved some filters to try and stop that if you're not actively looking for that. And then prompt and seed blending is an interesting one. So that lets you do multiple prompts weighted and kind of move between them. So you can go from Hulk to Superman more smoothly rather than just it being a binary. Okay, so last demo. Okay, so this is a little playground we built out to try and show people what stream diffusion can do and let them play around with the different settings, almost like a learning thing. But over on the right, you've got the input. This is just like a little JavaScript thing generating some interactive fluids. But you can see how it lends itself really nicely to these artistic effects. Right? You can, if we change the prompt and add in fireworks, you can. This is the thing I was talking about, where you can adjust the weight of the different prompts. You can also, again, you can use the camera. Like the first thing everyone does, like across everyone that uses it, is just go and type Trump or Musk. You can make yourself look kind of like Trump. But again, like this, this model that we're using is called SD Turbo. It's better suited to the artistic stuff, but some of the newer ones, so SDXL, are more focused on facial, like photorealism type stuff. So you'll get different effects with different models. It's fairly complex. You can play around with the different control nets. and get all sorts of different kind of effects through that. Cool. So what's next beyond this? One of the interesting areas that I've seen a lot of stuff happening in is 3D world state. So a lot of that's in the context of game generation, like making these open world games. But I think like having the models be able to represent physical state, it might bleed into some of the video stuff as well. Like it's one way that we might be able to ensure more consistency of output if the model understands the physical space better. Obviously, it's moving really fast, so lots of optimizations coming. The stuff that's running on H100s now is probably going to trickle down to consumer hardware soon. I think probably everything converging as well. So those two examples of like the different definitions of real time I gave at the start are probably going to go away and kind of merge into one. And then I think also like one thing we've noticed is that it's hard to, as you saw with that example just then, it's hard to make a generic like one-size-fits-all solution for this stuff. So I think probably as people find use cases for it, we'll see more targeted, more specifically trained versions of this stuff emerging. And then post-generation upscaling and refinement as well, I think is interesting. So one option would be to use these models to generate like your rough, raw video, but then use something more powerful to refine that and turn it into something consumer-facing or like more visually appealing. Okay, that's it. So you can try that thing I was just doing, daydream.live. You can play around with that playground. It's free. It's open. You can join our Discord where we have lots of artists and builders hanging out and talking about this stuff. And also email me if you want. Thank you.
Questions?
Thanks for the impressive demo. Can you use more than one GPU at the time for generating one image, or is it parallelized at that level?
Yes. So within stream diffusion, no, but yeah, within a lot of this stuff, yeah, it is possible to spread it across different GPUs. And that's what a lot of these newer gen models are doing. They're spreading across multiple GPUs.
Everything was very clear. No more questions.
Yes.
Thank you very much, Thom.
Perfect. Thank you.
Phil. Ren.
Does the microphone work? Ooh, the microphone does work. Hey, that's great. It's a good start. Okay, I remember to mute it and everything. Wouldn't be the first time. Oh, no, come on, one more. There we go. Okay, perfect. Okay, thank you all so much. Am I last? There's no more? Okay, perfect. Thank you all for staying around to hang around with me. I'm going to talk a little bit about what is probably the most word soup title I've ever written, which is AI-powered just-in-time per title encoding. A little bit about me first. Hey, I'm Phil. If we haven't met before, I've met a bunch of you, not all of you. I'm Director of Product Strategy at MUX, whatever that means. I'm still trying to work that out exactly. But I spent the last 3 years running MUX Video from a product management standpoint. And I've been in streaming video for about 15 years. I worked at the BBC and at Bright Cove, and I worked with Thom at both those places as well, and it was amazing. So didn't realize, I think we discovered, very late in the process that we're both speaking at the same event, so that was great. I have kind of worn every hat over the years, engineering, product, DevX, tooling, all those sorts of things, support, which is probably the most painful one, but mostly now I work on AI strategy and AI prototypes for new things we want to build. I also run London Videotech, so kind of a London version of this. If any of you ever want to come, give a talk, email me, I would love that. I also organize this little conference called Demuxed. Demuxed is going to be, by the way, I love that this is like an anamorphic widescreen. really made me happy. Demux is the 29th and 30th of October in London. We've got 35 speakers from across the industry, some amazing names there, and there's also loads of other events in London that same week. We've got FOMS the day before, got Videoland Dev Days the weekend after, and we've got GStreamerConf the couple of days before, weekend and a couple of days before. If you want to come to this, look how beautiful it is. Look at this beautiful space. I'm so excited to go there. I actually took this, you can just about see a BFI. I took this photo on my way back over the bridge after the first time I looked. Beautiful venue. It's going to have it's a Dolby grade cinema and Dolby grade screen. But all I'm asking you is buy your tickets now because they will sell out and I don't have spares and people are going to be grumpy if we run out. If you're interested in sponsoring as well, a couple of very special packages left. Imagine this, but with your name on it. It could be yours, right? That's not what I'm here to talk about. I'm here to talk about Mux things. So, a little bit of background. You need a little bit of background before I get into this one, just like Tom's. First one is a little bit about Mux Video. Mux Video is an API product for building video infrastructure. Really simple API for live video and on-demand video. It scales as you grow, very affordable, and we work with a lot of software customers, right? Not media customers. We work with people like Patreon, HubSpot, Substack, Synthesia, those sorts of people who are building software products with video features, not necessarily traditional media companies. Very different, as I painfully found out when I was product managing. Mux Video uses something called just-in-time video encoding. So when you upload a video to Mux, 80% of those videos don't get upfront transcoded. They just get transmuxed, stored, and then when a customer or a viewer comes in, tries to play that video, that's when we transcode the bits of the video, segment by segment as they're requested. This means that we, I would say, have the best time to publish in the industry, means that we can publish 60 minutes and 40 seconds, which is pretty good. It's complex though, like obviously it's not a simple architecture to do that. It has downsides. Everything has benefits and trade-offs. Quick hands up and down. Who knows what per title encoding is? Okay, good, about half the audience. Cool, perfect. So per title encoding, about 2015, Netflix put this paper out which basically said, not every video is the same. You shouldn't encode every video the same, which seems completely reasonable. Fundamentally, some videos you're going to be overspending on bitrate, some videos you're going to be underspending on bitrate, therefore you're either sacrificing quality or cost. It's a pretty simple trade-off. There have been a ton of ways of building per title encoding. A ton of companies have built per title encoding over the years. I'm going to tell you why building per title encoding plus just-in-time encoding is hard. So that's your background. Now I'm going to tell you a story, because everybody loves a little story. Back in 2018, 2019, so per title encoding 2015, okay, cool. So a couple of years later, John, our CEO, is like, we should build per title encoding. Seems completely reasonable, right? So we said, okay, let's go build it. Cool. There's kind of 3 buckets of approaches to per title encoding traditionally. First one is brute force. Take a bit of a file or take all the file, run a ton of encodes, pick the one that scores the best with like a quality metric, whether you use VMAF or whatever, it doesn't matter, but just run a ton of encodes. That one looks good, we're going to use that one. That's one approach. Obviously, there's pretty big trade-offs there. It's very expensive, very time-consuming. But if you care about, actually like huge amount of investment in like a lot of media, might be the best approach. Next one is content categorization. So take the content, work out what it is. It's like, hey, this is a football match. Cool. I know what a good encoding ladder is for a football match. This is like content matching. What's really important here is like, don't just take the first like minute of the stream, because for a football match, that's probably just a slate that like has some text on it, and then you've matched against the wrong content. Very common mistake, but yeah, like a content matching approach. Third approach, actually like do deep analysis of the media, dig into it, work out what it is, work out what the best actual encoding settings are for it. We did this one, but with AI, the first time round, and it was hard and had downsides. This is what Mux's ingest pipeline looks like. It's really simple. So we download the input file, we run some basic structural checks on it, we check things like the codecs, the resolution, the bit rate, the GOP structure, the GOP length, all those sorts of things. But we don't do a full decode because that's slow. And then we just transmux it. We transmux it to a TS. Actually, it's segments of TS, but they're bigger segments than like a streaming segment, but like much longer. And then we upload them into media, and then you can publish it. remember, just-in-time media transcoder, when somebody hits play, gets a segment request, great. I'm going to pull out a chunk of that, just-in-time encode it, and deliver it to a viewer. So we added AI-powered per-title encoding to this. Really simple, right? So during the structural check, we also decoded media, built a model that could predict convex hulls, which is one of the traditional ways of building per-title encoding models, and then stored that proposed ladder, ABR setup, bit rates, all that sort of thing, so we could use it when we just-in-time encode it. Cool. Simple. We shipped it. It was great. 2018, 2019, we iterated on it. We added a closed feedback loop from the product we have called Mux Data, which is a way of monitoring video streams, so using kind of customer data to then iterate on that adaptive bitrate. I've done a few talks. You can hunt out talks of my name about this architecture. I did one at EBU. I think I've done Seattle maybe even. In fact, I'm pretty sure I did one in Seattle thinking about it. Anyway, I did a bunch of locations. I won't go into depth. It worked okay most of the time. But sometimes it got it really wrong. Wasted bandwidth quite a lot. Wasn't great at kind of finding best optimizations. When it made bad mistakes, it was really bad. Like really underestimate bit rate, and that's pretty bad to explain to a customer. It was really complex and quite high maintenance. There was a lot of machine learning involved in the ingest process. It was very hard to maintain, and it obviously introduced full decode, which made it slower to ingest content. So you're probably thinking, okay, so it had bugs, right? We work in software, right? You just iterated and fixed the bugs, right? Don't know if you remember this happening. COVID kind of happened early 2020. So like as we were trying to iterate on this stuff, the whole industry kind of changed and our priorities changed, right? The whole industry had this hockey stick moment where suddenly we're doing huge scale, we're doing live events, everyone's doing live conferences, and suddenly the industry is in this big explosive moment, which is great for a while. So we moved our focus, right? We moved on to reliability, we moved on to scale, we moved on to live-centric workflows. So we didn't iterate on per title and audience adaptive. A lot of people moved on to other projects, which happens a lot in the startup. And then we had these big post-pandemic corrections across the industry, which just meant that we weren't able to invest in that project. So that's your backstory. That's the first time we built per title encoding. Shall we talk about the second time we built per title encoding now? So good we did it twice. 2023, 2024, John said, we should build per title encoding again. He's right, we absolutely should. And guess what we said this time? Okay, let's build it again. Disclaimer here, I worked heavily on this, but Justin, my wonderful colleague, worked on Zencoder, now works at Mux with me, worked on a huge amount of this. A lot of this is his work on the underlying piece. He does an amazing job. But cool thing is, with having got it wrong once, that means you get a set of requirements for the second time you build it. Here's the first one. Got to measure perceptual quality on an ongoing basis, right? That was one of the things we were learning when the first time it went wrong. Is like, we didn't know when it was getting it wrong. You've got to measure it constantly and constantly iterate on it. You can't slow down ingest by meaningful amount. That's a hard requirement. Like, yeah, reduce it a little bit, totally fine. Don't dramatically blow it up. Lean into AI, because like some of that stuff was really, really promising, so we want to do that again. We need really strong guardrails against getting it deeply wrong. Not only do we need to know we've got it wrong, but we need guardrails against it happening. And then like a simple, maintainable architecture. There's a whole thing about not every customer actually wanting the same trade-offs when it comes to per title encoding we'll get into, but it's also got to be cost effective as well. Like we don't want to blow up financials here. Cool. Some of these I take a while to talk about, others I fly through them. Don't worry. I know I'm standing between you and beer. I know how it is. So first one, measure perceptual quality and bit rates on an ongoing basis. So we started here, and we basically said, how can we measure a perceptual quality estimate on every single segment that we encode? And bearing in mind, we encode hundreds of millions of segments a month of video. How do you work out like a scalable way to do that? Okay, well, we'd love to use VMath, but VMath is slow and really expensive. Like doing that for every segment we JIT would cost like over double our COGS for encoding, because VMath is slow and expensive. So what's cool is X264 gives you per frame SSIM in the encode loop. You don't cost you anything to get that out of the encoder, so we should do something with it, right, was our approach. Like, let's start there, see if it's good enough. So we pull out effectively a per segment average and then percentiles for every single segment. So that's free, great. We need to put it somewhere. We put it in 2 places, actually. We put it in Grafana for short term, so the last 30 days stays in Grafana, and then we also put it in a data warehouse. Ours happens to be Snowflake for long-term analysis, and obviously the reasons become clear when we talk about data training, those sorts of things. But we also need to store the bit rates, because that's the other piece of this puzzle. We need to know what bit rate creates what SSIM values out of the encoder on a per segment basis. Here's what it looks like in Grafana. So the left-hand graph is like SSIM values. So arbitrary line, we can debate this line, 0.98 at 1080p. So you want to be, our target was like be above 0.98 SSIM score at 1080p on the average for the segment. Obviously you can see here the 1080p rendition is actually this green one. So for this is per segment, so each data point is a segment of this video, it's not per frame, so as we move through the video, yeah, the 1080p stays above SSIM 0.98. So that's good. You're probably going to ask me why it stopped, why some of the lines stop. Well, some of the lines stop because nobody's watched those renditions. So we only generate the SSIM quality data when somebody watches it, because that's the only time we're encoding it. So it's the only time it actually appears in our metrics. So if something's unwatched, we don't have quality metrics for it, which at our scale we kind of need to do. Then we've got the bit rate as well in much the same way. You can see exactly kind of the target bit rates that we ended up with on this video. It's just the exact same situation with why the numbers stop. Obviously, you can kind of tell from this graph it's like a bit of a CRFE encode as well, especially at the high end, but that's a whole of the presentation. So that's the first bit. We've got loads of data now. It's flowing into data warehouses. We can do analysis on it. We can understand where we are. We have a starting point. So the next one is trying to work out how we don't slow down ingest by anything meaningful amount. This is where it gets super weird. How can you work out what's in video content without like actually decoding it? Kind of hard, or like at least like going really deep on an analysis of it. How can you find like a really quick way to work out like how complex is really the question, right? It's not about what's in it. That's one way to approach it, but it's about how complex is it? Because complexity is what maps to how you need to adapt your encoder overwhelmingly. So the question became, how can you predict the complexity of a video without deep encoding? Here's how we did it. We used the quantization parameters of the file that we're given. Hands up if you know what a H264 quantization parameter is. Crap. I was hoping more people would know this. QP determines, basically, here's my approach to it. This is like the trade-offs that the encoder has made when it encoded a video. There is a quantization parameter on the per frame, but what I'm talking about is quantization parameter on each macro block, right? So 16 by 16 pixels, how hard was the encoder working when it encoded this macro block? But that's only important if you also know the byte size of that macro block, right? You can't just do it for how hard the encoder was working, because like maybe the encoder was overstretched. Like, there's a bunch of kind of complex reasons here, but you need to know both the size and also the exact QP value of that macro block. This turns out, as long as you trust the encoder that came before you, at least at some level, to be a pretty good estimation of complexity. This falls into like 4 buckets. One is like a small byte size with a low QP, low complexity, or it just wasn't important, so you don't have to worry about compressing it too much. Small byte size, high QP, it was really compressed. Now there's 2 paths there. Either it's unimportant, or you're hitting what you can do with the bit rate of the encoder that came before you. Large byte size, low QP, we didn't compress it, it was effectively how it was when it came in. So it was probably bandwidth wasted there. And a large byte size and a high QP, very compressed, but also very complex, probably meaning you're like hitting the boundaries of like what the encoder was capable of doing. So you're probably, if you looked at it, see artifacts on a very high byte size, high QP macro block. I'm going to show you a demo of what that looks like. Or at least I'm going to try. I'll give it a shot. This is a very hacked X264 inside FFmpeg, and written like just a visualization of every macro block's QP value. So the more densely shaded the QP is, the higher value. Has anyone worked out what the video is yet? It is indeed Big Buck Bunny, and you're just watching it through the QPs on a macro. There you go, the title does catch up. You're just watching it through the QP values for each macro block, which is quite good fun. You have to like really zoom out of this, and you really have to squint to see it, but you do just get his face appearing. I'm going to move on to slides in a second. I should have run this at 2x, really. There you go, there's his face, and there's his ears. So here he goes, coming out. There you go, you recognize him there, he's coming out of his cave. So yeah, so that is like a little visualization. That like is effectively in the product at this stage, because that same kind of fork of x264 that dumps the QP values is how we then build the whole thing. This is what that analysis ultimately outputs. It outputs a JSON blob of like statistical sampling of quantization parameters. So you can see here for each of P frame, I frame, B frame, and then average across them all, what the QP values were at each percentile, and the byte sizes as well. So we've got a ton of data now, which is what we're looking for. I called it SSQP there. That stands for, and this is a backronym if I ever saw one, statistically sampled quantization parameters. Although we called it stupid smart quality for pictures at one stage in the development process, which I think was a little bit more accurate. And this only looks at frame structure, right? This is not decoding content completely. This is not looking at the actual content in the frame. This is just trying to interpret the intent of the previous encoder that came before us, how complex that image was that it looked at. All with me? I promise the AI stuff is coming. Third bit, lean into the AI. There's good stuff there. You probably see where this is going, right? So we've now got this massive set of data of SSQP structures, right? For every segment that we're encoding, we're pulling out this, for every input that comes through, we're pulling out this SSQP data for the media. And for every segment we're encoding, we've got quality metrics, right? We've now got a massive data lake of it. We've got hundreds of millions of data points. That is something you can train a neural network to look at, right? This is what AI is built for. It's built for finding patterns in huge data structures and huge data archives. So what it really boiled down to is what model should we use to represent this data? We ended up on a random forest regression model. Your miles may vary. Obviously, this is kind of a more traditional machine learning model as opposed to like a more modern model. A random forest model, it's a bunch of decision trees, takes the average of those decision trees, and makes predictions, kind of get to a final result. It's pretty good. It's great at handling this sort of data structure. Works really well for this exact use case. There are downsides on where this doesn't work. Some of them are, this particular model can't really predict outside of the bounds of its training data, which is probably one of the bigger downsides. Like if it's never seen something like this before, it's going to struggle. Generally, though, at our scale, we probably see every type of media you could realistically see. There are outliers, but generally this works well for us. An SVM would work really well in this case too. They were pretty much toss-up from like a performance and a testing when we experimented with it. So we ended up on a random forest regression models. Here's what it looks like. So to train it, we use a tool called Hex. Has anyone used a Jupyter notebook before? Yeah, it's like a hosted Jupyter notebook, as far as I can tell, which we pay an awful lot of money for. But anyway, then we use sklearn random forest regressor, which is just kind of in your standard Python machine learning toolkit. And then all of that data we put in Snowflake, that's where the training data comes from, gets pulled into that Hex notebook, and then that runs through the sklearn, which kicks out a PPML model, which is XML that I never ever want to look at again. It was a lot, and we also had to write our own Go module to interpret it, which was also not ideal. Then applying that model during ingest is actually pretty easy, so it looks quite similar to our previous attempt. During the kind of structural check, we extract the SSQP values, that JSON blob you saw before. We stick that, well, the first thing we do is use that to predict the 1080p bandwidth we need effectively. So pass that SSQP model pass that SSQP data into the model. Model gives us back, hey, you need a 1080p around this bit rate. We actually then translate that into a multiplier for complex reasons, and then apply that across the ladder. So we've got kind of a standard ladder for 1080p, And then those multipliers that we've ultimately got out of a model is how we manipulate the ladder up and down and wider and thinner to fit to that particular piece of media. And then we just store the multipliers, because we'll need those multipliers during JIT. We store the multipliers because that means that if we update our standard ladder, the multipliers still apply nicely. So if we say, hey, actually we need to bump all the 1080p's, you don't have to go through and retroactively kind of update the whole database. You just kind of bump it, and then all the modifiers just take effect from there. Here's what the modifiers kind of look like. You get kind of a proposed multiplier and then an effective multiplier. This is just like a little bit of fine-tuning we've kind of applied to the model over time as we've gone, said, hey, you know, this is a way of, if we want to tune the model slightly towards bandwidth saving, we can tune like the proposed multiplier to like the actual multiplier that gets applied. Or if we want to tune the model to quality, we can decrease that multiplier, which should kind of make it a little bit higher quality, which is nice. And yeah, this is the other piece that just gets saved in our data model. Pretty simple. I only had 25 minutes. There's a ton of really deep stuff here. I could easily spend 30 minutes talking about how CRF fits into this, because under the hood, this is also a capped CRF encode. So we're also taking into account CRF there. Also, like every jittable codec needs its own model, because QPs are different across different codecs, DCT codecs. Yeah, and obviously your model is different for 1080p versus 4K top bit rate as well. So there's a lot more detail here that, yeah, would be talks on their own. Cool, we've got AI stuff. Great, we did the AI bit. Next one, have strong guardrails against going wrong. This one's actually pretty simple. The great thing about using multipliers, you can just put bounds on them and just say, hey, never go above 2x. Right, it's kind of a hard line on the right, and there's a pretty hard line on the left as well, for nothing below 0.6. Sometimes the model will say, if you give it a waterfall, it'll say, you need 10 times the bit rate for this, my friend. And you're like, no, because nobody will be able to watch it. Or like, there are often times where you're making trade-offs for like viewability or cogs that the model isn't aware of, right? The model doesn't actually need to be aware of. We treat that by using bounds to constrain the model a little bit. We also have minimal multiplier. That mostly exists for screen recording content use cases, because that's kind of the downside of using complexity as a measurement. Screen recording is not complex, it's just detailed, and you want to retain that detail. So like, it's kind of, there's a difference between like doing a single headshot video that like would also be like really low complexity, but actually looks fine to viewers. But like when it's screen recordings and you've got like a lot of text on it, you need that fine detail to come through. So like some of the clamping at the bottom is to try and make it a little bit better for screen recording. Cool, so we've got guardrails. Is it a simple, maintainable architecture that's easy to iterate on? Kind of, actually, yeah. We didn't really have to change like the JIT pipeline at all here. All we have to do is read that extra metadata, apply the multiplier to what bitrate we're targeting. No real changes there. Same to our manifest, just generate it based on the multiplier. It runs really safely, which is what's nice. Like, there's a nice bailout here of like, hey, if there's any problems in the prediction or the AI piece of it, just apply a standard bitrate ladder. We'll worry about it down the road. It still plays. Everything's fine. Maybe we don't get the perfect quality, or maybe we don't get the perfect bitrate, but better than failing. It's pretty low maintenance, other than like iterative training on the data models. We've now got several years worth of data, so you know we can look at massive data sets here if we want to. But other than that, it's pretty simple. But that beautiful hex workbook that I was like, oh, it's just a button. It's kind of not just a button. It's this goes on for 15 seconds. It is a lot. So yeah, like obviously we've done many iterations of this. We've learned where the rough edges are, and overwhelmingly where the time was spent in this project was iterating on the training of a model, removing data that was obviously problematic, or maybe a bad encoder that maybe didn't do the sensible things with QPs that we would expect it to do, those sorts of things. Cool, pretty maintainable if you don't look too closely at hex. This is where it gets interesting, because not every customer actually wants the same trade-offs when it comes to per title encoding. I work with a ton of customers, and one of my favorite things is actually spending time with customers, sitting, talking to them, understanding their use cases. I have customers who have videos where they do not care about quality at all, and the same customer in a different use case in their app want the absolute highest quality possible video. It's not a one-size-fits-all solution. And we probably, at least my opinion is, you shouldn't use the same per title encoding setup for each of those. like a great example here is like a social media company who's just building like a scrolling app is going to make a very different quality versus cost trade-off to a media company. And we have both of those at Mux on a daily basis. How did we do this? We built something called quality levels, which is effectively tell us how much you care about the quality versus cost trade-offs of this video every time you put a video in. And it's effectively 3 targets. If you've ever worked in product management or pricing product, you've probably heard of good, better, best pricing. This is exactly what this is. We have a good mode, which is also free encoding, no cost, and that's called basic for us. You get kind of free bitrate ladder, free rung bitrate ladder, very simple, but it works well for a huge amount of use cases, especially for social. Then we've got plus, which is better. You start paying for encoding at that level. And then you've got premium, which is you pay about 1.5 times more for encoding and delivery there, because the bit rates are going to go up. But you tell us that, and you tell us that on every asset. So if you're that company I mentioned earlier who's got this like social feature, they do all that social feature on basic, and then all their marketing videos are on premium. They get to pick what quality target they want. It's actually the same model, interestingly, but the quality level kind of impacts like the bitrate ladder shape, the initial bit rates that we're offsetting from, and also the CRF targets as well. Again, CRF could be another 30 minutes here, so let's not talk too much about that. Cool. Not every customer wants to make the same trade-offs. Great, that one's done. Be cost effective. Is it cost effective? Oh no. Oh no. Oh no. Apparently I forgot to copy in the latest slide. Okay, that's bad. Okay. There's 3 components to this, so middle bit's kind of right. Storing up perceptual quality data has some cost, but we also use Snowflake a lot for a lot of things. And we are also a media company. We store an awful lot of video. On the grants, that's a message to say your time is up, Philip. There we go. It should come back. There you go. On our grand scale, it's not actually that much money. Training costs, negligible, but we also don't run it frequently, like maximum once a month we go back and regress it, so it's not that expensive. Takes about 30 minutes to build a new model, to do a month worth of data. So, obviously, if we did 12 months of data in the next training set, yeah, that's gonna be, a few hours of training, but that's not actually that much. All just runs in Hex and Snowflake. And the execution cost during ingest is really negligible. It doesn't really cost anything, because we're not, compared to our previous models where we're kind of decoding the content, passing that to a machine learning model to talk about like what the actual content is and how we should encode it best, that's like a lot more overhead. So for this, it's virtually none. I cannot believe I put an extra slide in about this, and now I can't believe I didn't get rid of this one. Cool. We've ticked all of our list. So does it work? Of course it works. Phil and Justin would tell you it works. Wow, I'm really stretched on that picture. Oh, great. Yeah, of course it works. It totally works. Most important thing to remember is everyone's aims for per title are different. Generally, it's on a scale, though. Some people just want to increase quality for the same bitrate. That is one of the core things you can do with per title encoding. The complete other end of the spectrum is decreasing bitrate for the same quality, right? Like actually just saving money. Most people are somewhere on the spectrum, because the middle one is I want to do a bit of both. Yeah, we're actually in the middle. We want to both, decrease our bitrate a little bit and increase the quality that customers get a bit. So we're in the middle of this tree. What does that look like? An average bitrate reduction of about 12%, an SSAM score increase of 0.005. It's actually pretty good. It's a log scale. And 75% of ingest experienced no slowdown at all, because we ran this in a shadowing mode for a very long time. 75% of ingest, no impact, published time. And when you combine that with quality levels, customers have stopped complaining about quality. So that's like the biggest measure as a product manager is like, have people stopped saying, I have quality feedback? Yes, great, we solve a problem, my perspective. Justin asked me to put some graphs in, so I put some graphs in. This one's fun because this is kind of across the year where we're rolling out per title encoding. V2, and you can see that the average bit rates come down right across this graph, but the P90 bit rate's gone way up. That's because before we introduced per title encoding, we were under encoding those videos. Those videos looked bad. right? At the 90th percentile of complex content, you had to increase average bitrate, like you just had to, because otherwise the videos weren't going to look as good. And at the bottom end, you've also got a significant reduction at the P10, right? So this is the low complexity content. This is the screen recordings, the boring headshot videos. So that we would expect the bitrate to go down on. On average, goes overall down, but we're doing a better job at the top and a better job at the bottom. And CRF goes up, not CRF, SSIM goes up a little bit. But that little bit is actually meaningfully impactful when you actually look at the content, I promise. And that's kind of it. How was I on time, by the way? Okay, okay. This is my cat, by the way. Isn't she cute? Thank you.
Thanks. Any questions?
Can you not give JB the microphone, please?
So, Phil, I'm going to ask you a tough question. I've been working 19 years at Harmonic. First question, why did you pick SSIM? Is it just because it was provided for free? Okay, yes. So if you talk to video experts, they don't even agree SSIM wave is good. People are more on the VMAF side. And as you probably know, company like Cinemedia, they have done the real-time VMAF estimate. Mm-hmm. And all encoder company have all their secret sauce. So I don't want to challenge you in public, but you should look at the literature. There are a lot of good papers, and I think it's a good direction, but you need probably to revise your SSIM dogma.
Yeah, absolutely. SSIM is good enough for what we're doing at the moment. I completely agree. There are better quality measures, completely agree. And I'm very interested in any fast approach to get to something that's approximating VMAF. Like, I absolutely am very interested in that. I'm also super interested in referenceless VMAF as well, which was a talk I saw somewhere recently. I can't remember where it was. But yeah, 100% completely agree with you. There are better quality metrics. This is about using what we had in the encode loop for free, more than anything else. Yeah.
What happens when you use a shitty encoder like X265? Instead of X264, which is a good encoder, do you see better gains than 12%?
So there's two interesting things here. 80% of what we get goes to standard input. The 20% that isn't standard input gets a transcode, like a CRFE transcode before it goes to us, before it goes into the exact same pipeline effectively. So we do just a simple transcode, then put it in. Right now, anything that's HEVC would go through that process. And the interesting thing is, in a week's time, that won't be true anymore, because we are starting to just-in-time process HEVC. We have to currently, one of the things we're actively doing is training a specific model for HEVC, and it'll be interesting to see if X265 output versus other HEVC that we get will be the same. But that is like an active thing we're doing now, is trying to work out what that model looks like for HEVC as standard input. So yeah, great call out. I agree. That's actively one of the fun bits.
Hello. Fantastic presentation, thanks. I just one very candid question. I'm not from the video environment. How do you know that a video is a screen content? And in your pipeline, where is it, like before the whole thing about getting your data about the bitrate, the SSIM, whatever? Advices.
Yeah, great question. We don't, is a simple answer. Like, we don't know it's screen content at the time. So the way we found that screen content needed like different handling was by looking at the outliers in the data. So we would go back and we would say because obviously I haven't got any graphs here, but there were like graphs where it's like, why is there like a bunch of videos where the estimator said we needed to be way down here, but like the PQ is way off? And then we would go find those videos, look at them, and, for example, realized, oh, this is screen recording content, when we looked at it with the human eyes and go, that is where we need to iterate on the model. Like, the model doesn't know it's screen recording content, it just knows it's like low complexity, but like high detail, essentially. Like it doesn't know what anything is, it just makes like statistical decisions. So like we only know from going and looking at it and then updating how we were doing the training to make better decisions. So yeah.
Okay, so just to confirm, you are able to cluster some outliers in your process, and you're just saying, okay, that's probably screen videos, let's have safeties.
Absolutely. So yeah, so we would like see like little like clustered batches on like when we're plotting like bit rate against quality, we'd find like little clustered batches of outliers. Then we'd like go and dig into those, look at the mezzanine and say, oh, it's screen recorded. We need to go and understand. We need to go and improve the training set for screen recording. Exactly.
Last questions. Was there any other use case, other outliers than screen as screen videos that needed some fine-tunings as such?
Great question. The only other thing that comes to mind is we did find some bad encoders that were like where the QP values didn't really like make logical sense, because yeah, we had this like 4 bullet point of like what a QP to byte size value meant, and we occasionally found encoders that were not making logical decisions there, and the best we could do there was basically exclude that encoder from the training set. So obviously we have some level of knowing, like, you know, there's enough headers in a lot of MP4 files about what created something. So there was some piece of media we just needed to exclude from the data set. But other than that, no content type, no screen recording it was probably the most interesting one. Yeah.
Jerry? Jean-Baptiste, the worse your encoder is, the better the CAE assistant is going to be. I give you a public information, the Qualcomm encoder you have on your Android phone. If you put a CAE encoder on the ARM core, you reduce the bitrate. Yes, but there's a beautiful business model, is that you put a software which is very light on the phone to reduce by 70, not 17%.
The second part of the debate is at the bar.
Yes,
thank you, Phil.
Thank you.
Thank you, everyone. So you can go for drinks. Unfortunately, we finished the drinks that Paris Videothèque is paying. We need more sponsors for more drinks next time, but you can pay for your drinks. Thanks.